This is Game AI Uncovered. My name is Paul Roberts, and today we're going to be looking at genetic algorithms. Imagine a world where giraffes started off with short necks, and as the number of giraffes increased, the foliage they could reach quickly got consumed, and only those giraffes with deviations from the herd, the ones with the longer necks, could reach the foliage and get to eat. So unfortunately, the giraffes with the short necks, well, they died out, whilst those with the longer necks, they survived. The trait of a longer neck then proliferated through the species, and you get the kind of giraffe that we see now. Now I've no idea if this is true, but it conveys the aspects of natural selection that genetic algorithms are attempting to replicate. In nature, we start off with an initial population. Each animal in a species does what it can to survive. Those that do get to reproduce and pass their genes on to the next generation, and so the species evolves. The genes of those animals that fail to survive and reproduce are lost to the species zoo. The animals then compete for survival and the process is repeated. So how do we do this in terms of computing? Well, we need to create our initial population, and this is made up of something called chromosomes. Then we allow the population to compete for survival in some way. This allows us to then score each chromosome, giving us their fitness values. If we have a solution whose fitness value is greater than some pre-specified value, we can stop right there. However, if not, then we select which chromosomes to use as parents based on these fitness values, and then combine them to create the next generation of solutions. We can then add some deviation to the population, like how the long neck was a deviation from the established trait of the short neck in the giraffe species. And then we repeat the process until we find the ideal solution, or until we reach some preset threshold, a time duration, a maximum number of generations. You can see the similarities between natural selection and genetic algorithms when we put the two flowcharts side by side. Genetic algorithms are a little more complicated than the natural selection flowchart, but the general aspects are the same. We start with an initial population, we then evaluate the fitness. For us, this is something like playing a level of a game or racing a car around a track, depends on the game. We then test to see if we have found our ideal solution. If not, we then select, cross over and mutate our solutions to produce child solutions. And then we repeat the process with the next generation. The only real difference is that genetic algorithms have a way of stopping evolution, whereas in the natural world, a species never wants to stop evolving. So let's take a look at what a chromosome actually is. Well, chromosome is the term used to describe a single solution to the problem. In the giraffe example, a single giraffe would be represented by a single chromosome, and a chromosome is made up of a number of genes. There can be any number of genes, it really depends on the problem you're trying to solve, but suffice it to say that each gene represents an aspect of your character, agent, or whatever you want to call it. For now, let's just call it a solution. In code, a chromosome needs to be able to represent all aspects of a solution to a given problem, good and bad. There are different ways to encode a chromosome, and this will depend on the problem you're trying to solve. For example, these chromosomes are binary encoded, so each gene is a 1 or a 0. Multiple chromosomes can have the same values in their respective genes. Remember, these represent an aspect of the solution. For a binary encoded chromosome, maybe each gene represents whether a particular aspect is enabled or disabled. Next we have permutation encoding. Chromosomes built in this manner all have the same values, but they're mixed up. This approach would be useful for problems like the travelling salesman, where each number could represent a different location for them to travel to. These chromosomes are built using value encoding. This means that they can store any value of a particular type. These top two are using floats, whereas the bottom two are using integers. As long as each gene is of the same type, it'll work fine. Finally, we can look at something a little more complex. These chromosomes are encoded using enumerations or enums that reflect a movement direction in a game. So maybe it's a pathfinding solution, the direction that an agent needs to navigate the environment. The bottom two take the idea a little further and are encoded using structs. This allows them to contain both an enum and a float, so this could be useful for a direction and a duration. Obviously, you can encode your chromosomes however you want, they just need to reflect all aspects of a solution. Okay, now we know what a chromosome is, let's generate our initial population. For this video, we're going to be using a driving game as our example. We'll have multiple cars, all with different setups, and each will be represented by their own chromosome. Each is being colour coded to help us keep track of them. So in the first instance, the genes in these chromosomes will be randomly set, and this collection is what makes up our initial population. The next step is to evaluate how good our chromosomes are at solving the problem. For us, this will be how fast can the vehicle get around the track. The faster the lap, the higher the fitness. The white chromosome on the left is for the white car and the blue chromosome is for the blue car. And we're going to keep things simple by having each gene represented by 2 bits. In reality, each of these genes would represent some part of the vehicle's setup and would be better encoded as floating point values. But that gets quite messy for a video like this, so stick with me. When they have completed their laps, we can put these chromosomes back into the population and add all the other chromosomes for vehicles we've tested. We can then visualise how fit they were by showing them as colour-coded bars on a fitness chart. Fitness in this context is how fast they completed a lap, and if any of them completed a lap faster than our desired lap time, we can stop there. Now we need to decide which of these chromosomes will become the parents for the next generation. So we're going to use a simple approach called tournament selection. We select a number of chromosomes and the fittest one wins that tournament. So in that example, the blue one wins, but notice that the white one was in that tournament but lost. In this second tournament, the white one shows up again, but it is the fittest. This allows us to have bad chromosomes with good genes go through, and we want that to keep our gene population as diverse as possible. So our parent pool is made up of all winners from all the tournaments. To create a child chromosome, we need at least 2 chromosomes to act as parents. To do this, we randomly select chromosomes from the parent pool. These are then removed to ensure we don't select them again. At this stage, we want all chromosomes in the pool to be used as parents. For this example, we're going to use the white and the blue chromosomes again. There are different ways to do this. This first approach is called single point crossover. Simply select an index of a gene in the parents. The first child is made up of all the genes before this index from parent A and all the genes after this index from parent B, and the second child is made up of the opposite portions. This method is called multi-point crossover. It's pretty much the same as single point, but instead we choose multiple points with which to cross over. As you can see, the 2 children are made up of opposite genes from the parents at these crossover points. The final approach, and the one we're going to stick with for the rest of this video, is called uniform crossover. This method sets multiple points with which to cross over, but the number of genes between these points is always the same. This example is very extreme, and mixing up genes so much will result in a poor crop of child chromosomes, but let's go with it for now. All children are then added to the offspring pool, leaving us with one final stage: mutation. Mutation is a simple process. Simply pick a chromosome with which to mutate, then select a gene within that chromosome and then change its value to some other random value. You can mutate more genes, but I'd recommend keeping mutations to a maximum of 5%. Any more than that and you can make the whole process of using genetic algorithms redundant. You'd just be randomly changing genes, which would result in a bad crop of parents for the next generation. Speaking of which, the offspring pool now becomes the population for the next generation. Remember, each of these chromosomes represents one of the cars we are testing, so with our new car setups, we can go racing again. So just to bring this all together, let's look at the genetic algorithm flow again. We started with an initial population, we then evaluated their fitness, raced around the track. Next, we check to see if we found an optimal solution. For us, this might have been a lap faster than some desired lap time for this track. If we haven't achieved this yet, we select the chromosomes to use as parents, we cross over to create offspring, we then mutate the required number of genes, and then we repeat this process with the offspring from the last generation becoming the parents for the next generation. This has been Game AI Uncovered. Thanks for watching. And before we wrap this up, a quick plug. If you want a more detailed explanation of genetic algorithms, check out Artificial Intelligence in Games. But for those of you interested in how the AI was made for release titles, check out the Game AI Uncovered series. All these books are available on Amazon now.